I'm about to show you a machine with no moving parts, no refrigerant, no electricity, and no chemistry that produces air cold enough to frost over in seconds. There's nothing inside it. Cut one open and you will find a hollow tube, a nozzle, and a small hole. That is the entire device. Compressed air goes in at room temperature. Out of one end comes air that can run 40 degrees below zero. Out of the other end comes air hot enough to burn you. Nothing was added. Nothing was removed. Nothing spins. Nothing pumps. And there is no refrigerant anywhere in it. Two honest things. Before we go further, because I am not going to spring either of them on you halfway through, the tube itself is genuinely cheap. A small industrial one costs somewhere in the region of $50 to $200 new, and a simple one can be made or bought for far less. The physics is real, it has been used in factories for decades, and it works exactly as advertised. The catch is what feeds it, and it is a serious one. This runs on compressed air, and compressed air is one of the most expensive things in any workshop. I will give you that arithmetic properly. And it is the reason this is not in your house, and one thing I will come back to at the end. Physicists argued about how this device works for roughly 50 years after it was discovered, and the explanation is genuinely one of the strangest things in engineering. I will show you what is actually happening in there, because once you see it, the whole thing makes sense. 3 levels: what it does, how it does it, and why you cannot cool your house with one. Let me start with the object itself, because it is almost absurdly simple. Let me describe the object, because it is almost absurdly simple. It is a tube, usually a few inches long, with a fitting at one end for a compressed air line. Inside, near that fitting, there is a chamber with a nozzle that fires the incoming air in sideways, along the wall of the chamber, rather than straight down the middle. That is called a tangential inlet, and it is the only clever part of the whole thing. Air entering that way does not travel in a straight line. It spins around the inside wall of the tube at an extraordinary rate. Figures commonly quoted for the rotational speed inside a working vortex tube run into the hundreds of thousands of revolutions per minute. Nothing is turning. The tube is solid. It is the air itself that is spinning. At the far end of the tube, there is a cone or a valve with a small opening in the center, called the hot end control. And back at the inlet end, in the middle of the chamber, there is a hole. That is it. A tube, a nozzle, a cone, and a hole. Air comes out of both ends. Out of the far end, past the cone, comes hot air. Out of the small central hole at the inlet end comes cold air. And the temperature split is not subtle. A commercial tube running on ordinary shop air will give you cold air commonly in the region of -20 to -40 degrees Celsius, and hot air well above 100 at the same time from the same room temperature supply. You can hold both ends at once and feel it, and it is genuinely startling the first time. Now, I know what a lot of you are thinking, because it was my first thought too. That sounds like it breaks the laws of physics. You put one thing in and get hot and cold out, with no energy input, no machinery, which is exactly what a perpetual motion crank would claim. So let me deal with that properly, because it does not break anything. The energy is coming from the compressed air. Compressed air is not free and it is not neutral. Somewhere behind the hose there is a compressor, driven by an electric motor, that did a great deal of work squeezing that air into a tank. All of that work is stored in the pressure. When you release compressed air, it expands, and expanding gas cools. That is the same reason an aerosol can get cold in your hand. And the same reason a bicycle pump gets hot when you compress air in the other direction. So the vortex tube is not creating energy. It is taking a stream of high-pressure air that already contains a lot of stored energy, letting it expand, and separating the result into a cold portion and a hot portion. Nothing is violated. The tube is a separator, not a source, which is why the honest question is not whether it works. It works, it is sold by several established manufacturers, and it has been standard industrial equipment for decades. The honest question is what that compressed air costs, and I will get to it. So where did this come from? The discovery is one of the better accidents in engineering. Around 1931, a French physics student named Georges Ranque was working with a cyclone separator, which is a device that uses a spinning airflow to separate dust from air. It is ordinary industrial equipment, and it has nothing to do with cooling. Ranque noticed that the air coming out of one part of the apparatus was cold. Not cool, cold. He investigated. He understood he had something unexpected, and he presented it. And the reception was poor. The physics establishment of the day was skeptical. The effect looked like it should not happen, and Ranque was not a senior figure. He eventually left the field. The device sat largely ignored for over a decade. Then, in 1947, a German physicist named Rudolf Hilsch published a careful, detailed study of the same effect, with proper measurements and a serious analysis. That paper is what brought the device to wide attention, and it is why the object is properly called a Ranque-Hilsch vortex tube. So the timeline is, student stumbles on it in 1931, gets dismissed. and a physicist rediscovers and legitimizes it 16 years later. And then, remarkably, the argument about how it actually works ran on for decades after that. There were competing explanations in the literature well into the latter part of the century, and papers are still published on the details of the internal flow. That is unusual. This is not a complicated machine, it is a hollow tube. And it took the scientific community an extraordinarily long time to agree on what was happening inside it, which tells you something about how counterintuitive the effect is. This is not a curiosity sitting in a laboratory. Walk into a machine shop, and there is a decent chance one is running. The main industrial application is spot cooling and machining. When you are cutting metal at speed, the cutting edge gets extremely hot, which dulls the tool and ruins the surface finish. The traditional answer is flood coolant, meaning a stream of cutting fluid over the work. Flood coolant is messy, it has to be filtered and disposed of, it contaminates the chips so they are harder to recycle, and it creates a health and housekeeping problem. A Vortex tube clipped to the machine, aimed at the cutting point, gives you a jet of very cold, dry air instead. No liquid, no mess, no disposal, and the chips come off clean. That is a genuine advantage, and it is why the technique exists. The second application is cooling electrical enclosures. Control cabinets full of drives and electronics generate heat, and they sit in factories that are already hot. You cannot simply open the cabinet because the air in a factory is full of dust and oil mist. So a Vortex tube fed from the plant's compressed air supply cools the inside of a sealed cabinet with no refrigerant, no compressor in the cabinet, and nothing to fail. In a hot, dirty environment, a cooling device with no moving parts is worth a great deal. The third is personal cooling. There are vests and hoods used by workers in extremely hot environments, such as foundries and glassworks, fed by a compressed air line through a small Vortex tube. It sounds crude, and it is genuinely effective when somebody has to work beside a furnace. And there are smaller uses throughout industry: cooling soldering operations, setting hot melt adhesives quickly, cooling test samples, cooling camera housings in hot processes. In every one of those, the same three properties are doing the work. No moving parts to fail, no refrigerant, an instant response with no startup time. It is worth being specific about why those three matter so much in a factory, because they are not the reasons a homeowner would care about. No moving parts means no maintenance schedule. A small refrigeration unit bolted to a control cabinet has a compressor, a fan, and a filter, and every one of those is a service visit and a failure waiting to happen in a dusty environment. A Vortex tube has nothing to service. You bolt it on and forget it exists. No refrigerant means no regulatory question. Refrigerants are controlled substances in most of the world, with rules about handling, leak checking, and disposal. A device that cools, using nothing but air, sidesteps all of that paperwork entirely. And for a plant with 100 cabinets, that is a genuine administrative saving. An instant response matters more than people expect. There is no startup delay, no thermostat cycle, and no minimum runtime. Open the valve and you have cold air in the first second. On a machine that only needs cooling while it is actually cutting, that means the cooling runs exactly as long as the cut and stops the moment it finishes. None of those three advantages help you cool a bedroom. All three are worth paying for on a factory floor. And that mismatch is the entire story of this device. Now the part I promised you, and I'm going to give it in plain terms rather than equations. Air enters through the nozzle and begins spinning around the inside wall of the tube, extremely fast, in a tight spiral traveling toward the far end. At the far end, the cone leaves only a small opening, so only part of that spinning air can escape there. The rest has nowhere to go except back the way it came. And here is where it gets interesting. That returning air cannot travel back along the wall because the outer spiral is already occupying that space. So it turns and travels back down the center of the tube inside the outer spiral as a second inner vortex heading in the opposite direction. Now you have two spinning flows occupying the same tube. An outer one heading toward the hot end and an inner one heading back toward the cold outlet. And they are in contact with each other along their whole length. The temperature separation happens between them. The commonly accepted explanation is that energy is transferred outward from the inner flow to the outer flow. The inner air, which is heading back toward the cold outlet, gives up energy to the outer air, which is heading toward the hot outlet. Why that transfer runs in that direction is where the decades of argument lived. The mechanisms discussed include the fact that the outer spiral and the inner spiral rotate at different rates, which produces friction and shear between them, and pressure differences between the outer wall and the center of the tube. The practical summary, which is what matters to you, is that the air is being sorted. The tube takes one stream and separates it into a portion that has given up energy and a portion that has gained it, using nothing but the geometry of a spinning flow. And the split is adjustable. That cone at the hot end is a valve, and opening or closing it changes what fraction of the air escapes hot and what fraction returns cold. Engineers call that the cold fraction, and it is the one control the device has. Turn it one way, and you get a large volume of moderately cool air. Turn it the other, and you get a small volume of extremely cold air. Same tube, same supply, completely different output decided by a cone. That is genuinely all the control there is on the entire machine. And the trade it controls is worth understanding because it is not a quality setting where one end is better. Set a low cold fraction, meaning you let most of the air out of the hot end, and the small amount of air that returns cold is very cold indeed. Excellent for chilling one small point, and useless for cooling anything with volume. Set a high cold fraction, meaning you restrict the hot end and force most of the air back through the center, and you get a much larger flow of air that is only moderately cool, better for cooling a cabinet or a surface. Total cooling capacity peaks somewhere in the middle, and the manufacturers publish curves showing exactly that. So the machinist chilling a single cutting edge and the engineer cooling a control cabinet will set the same tube completely differently, and both are correct for their job. That one cone is doing all of it, and there's nothing else to adjust anywhere on the device. Now the arithmetic I promised, because this is the honest heart of the video. Compressed air feels free in a workshop because it comes out of a hose in the wall and nobody sends you a bill for it directly. It is not free. It is generally regarded as the most expensive utility in a factory per unit of useful energy delivered. The reason is that compressing air is deeply inefficient. When you compress a gas, it heats up, and unless you deliberately recover that heat, it is dumped to the atmosphere. That heat is energy your motor paid for, and you never see again. A rough figure widely used in industry is that only a small fraction of the electrical energy going into a compressor ends up as useful work at the tool. Estimates vary with the system, and the message is consistent. Most of it is lost. Now put a Vortex tube on the end of that. A typical small industrial tube consumes something in the region of 10 to 40 cubic feet of compressed air per minute. To supply that continuously, you need a compressor of real size, drawing kilowatts of electricity, running constantly. And in exchange, you get a jet of cold air suitable for cooling a cutting tool or a small cabinet. Now compare that with an air conditioner. An air conditioner is a heat pump, and a heat pump moves several units of heat for each unit of electricity it consumes. Modern units achieve a coefficient of performance of 3 or 4, meaning 1 kilowatt produces 3 or 4 kilowatts of cooling. A Vortex tube system, counted honestly from the wall socket, is dramatically worse. It is not close, and it is not a matter of refinement. The physics of compressing air and then throwing away most of the stored energy simply cannot compete with a heat pump. So here is the honest verdict on the title. You cannot cool your house with this. Not because it does not work, but because the compressor feeding it would use far more electricity than the air conditioner you were trying to replace. Anybody suggesting otherwise has not counted the compressor. Which raises the obvious question of why industry uses it at all. And the answer is precise. Industry uses it in exactly the situations where the compressed air is already there, where the cooling needed is small and local, and where the properties of the device, no moving parts, no refrigerant, instant response, tiny size, survives dirt and heat, are worth more than the energy cost. Cooling a cutting tool is worth a lot of compressed air. Cooling a house is not. That is the whole story. And it is a good example of a technology being genuinely excellent within a narrow band and genuinely wrong outside it. So what can you actually do with one? If you own a compressor, there are real uses, and they are worth knowing. Spot cooling while machining or grinding, exactly as industry does it. If you cut metal in your workshop, this is the application it was made for. Cooling something small and specific in a hurry. Setting an adhesive, cooling a part you need to handle, chilling a component for a shrink fit, cooling yourself while doing hot work in short bursts. And that is a genuine use in a hot workshop and demonstration, which I do not say dismissively. If you have children, this is one of the most convincing physics demonstrations you can put in someone's hands. One hose in, hot out of one end, cold out of the other, and nothing inside. What it is not for is running continuously to cool a room, a shed, or a greenhouse, because your compressor will be running continuously to feed it, and your electricity bill will make the point for me. If you want to buy one, small Vortex tubes are widely available from industrial suppliers, and the general purpose ones are not expensive. Check the air consumption figure before you buy, and compare it against what your compressor can actually deliver continuously, not its peak rating. That is the mistake people make. A small workshop compressor that runs a nail gun perfectly cannot feed a Vortex tube continuously, and you will find yourself with a machine that cools beautifully for 90 seconds and then waits for the tank to refill. Now the honest limits, and there are 6 of them. The first is the energy cost, which I have given you and will not repeat. The second is air consumption, which is the practical version of the same problem. Match the tube to your compressor, or you will be disappointed. The third is noise. These are loud. Air at high velocity through a small orifice produces a genuinely piercing sound, and running one at a bench without hearing protection is a bad idea. Mufflers are available and they help. The fourth is that it produces a jet rather than an atmosphere. This cools a spot. It does not cool a space, and pointing one into a room achieves very little. The fifth is moisture. Compressed air carries water, and when you drop it to -30 at the outlet, that water freezes. A tube fed with wet air will ice up and choke. If you're going to use one seriously, a dryer, or at least a good water separator on the line is not optional. And the sixth is that the cold output is small in volume. Even at full flow, you're dealing with a modest stream of air, and it feels far more impressive on your hand than it is in total cooling capacity. Before you go anywhere near one, the safety, because compressed air is not harmless and it deserves the same respect as any pressure system. Never direct compressed air at skin at close range, and never at anybody as a joke. Air forced into the body through the skin or any opening causes genuinely serious internal injuries, and people have been killed by it. This is one of the oldest shop floor safety rules, and it exists because of real cases. Wear eye protection. A jet of air at that velocity picks up chips and dust and throws them. Wear hearing protection, because these are loud enough to matter over a working day. Mind both ends. The hot outlet gets genuinely hot enough to burn, and the cold outlet gets cold enough to cause a cold burn on prolonged contact. Neither is obvious to somebody picking one up for the first time. Use hose and fittings rated for your working pressure, secure the tube so it cannot whip about, and drain your compressor tank regularly, which you should be doing anyway. So this week, here's what I want you to do, and none of it requires buying anything. First, if you own a compressor, go and look at its rating plate and find its continuous delivery figure in cubic feet per minute, not its peak. Write it down. That single number decides whether a Vortex tube is usable in your workshop or a toy that runs for 90 seconds. Second, feel the physics for yourself with something you already own. Hold an aerosol can and spray it for 10 seconds and feel it go cold in your hand. That is expanding gas cooling, and it is the same principle sitting underneath this entire device. Third, if you have a compressor and you cut metal, look up Vortex tube spot cooling and see what it does to tool life. That is the one application where the energy cost genuinely pays for itself, and it is the reason machinists own them. Tell me in the comments whether you have ever actually seen one running and what it was cooling. I read every one of these, and I suspect the answers will be almost entirely from people who work in machine shops, because that is where they live. Here's the thing worth keeping from all of it. In 1931, a student made a mistake with a piece of dust-separating equipment and noticed the air was cold. He was dismissed. 16 years later, somebody else measured it properly, and the device entered engineering, and physicists then spent decades arguing about what was happening inside a hollow tube with no moving parts. Today, it sits in machine shops all over the world doing one job extremely well, and it will never be in your house because the compressor behind it eats more electricity than the air conditioner it would replace. That is not a failure. That is a technology that found the narrow place where it is genuinely the best answer on Earth, and stayed there. And there is something worth taking from that, which is that a device being remarkable and a device being right for your problem are two entirely different questions. This one is unquestionably remarkable. For cooling a house, it is unquestionably wrong. Knowing the difference is most of engineering.